So this week, we continue our journey through the neural network session. So last week, we built a foundation, right, by reviewing multi-layer perceptron, backpropagation, and word embeddings. So this week, we talk about how to represent a sequence, okay, using neural network. So we are going to discuss a few things. So first of all, an overview. So how you can build a classifier using a neural network only, okay? And then we will discuss several technologies to put a sequence of embeddings into one dense representation, okay? And finally, we will talk about several ways to train a neural network. So what I mean is how to improve SGD, okay, in training a neural network. So first, let's take a look at the classifier again. So in week 3, we talked about an n-gram language model and a naive Bayes classifier, right? So now it's week 9, and we know how to build a neural n-gram language model, right? But we don't know how to build a neural text classifier yet. Okay, but you said we learned multi-layer perceptron, right? So to replace a single layer perceptron, that's what we did last week. So when we have a representation of a document, right? So we pass it through single layer perceptron, be it perceptron or log linear model. That's a neuron. And last week, we know we can put it through multi-layer perceptrons to learn more powerful intermediate hidden layers, right? To improve the nonlinear separability of these classifiers. But there's a difference between the neural n-gram language model and the neural text classifier we learned, which is the input. So if I flip back, you can see that the neural n-gram language model uses word embeddings as inputs, right? But this text classifier we built last week uses, say, TF-IDF representation of a document. That's the difference. That difference is significant because, first of all, the input layer and the hidden layers, they don't look similar. Right? Now, I draw it because the input layer is either black or white. It's very sparse. Okay? But the hidden layer is dense. Every neuron has a value, right? A real value. Second, more importantly, we have to manually define this input representation. But for word embeddings, we don't. And it's automatically learned. So just recall what we learned last week, right? So if we have a one-hot representation of a word, X, we put it into a neural embedding layer. Or we can also understand as we multiply that, okay, with a embedding lookup table, right? And we turn that into a dense vector. So these embeddings, okay, they are dense, they are like hidden layers. They are low dimensional, okay, not on the scale of a vocabulary size. And more importantly, they are automatically learned. You don't have to manually define the feature templates, okay? So they're more like the hidden layers. So can we replace the input of the text classifier with word embeddings? And we got something like this. So every word, we make a one-hot representation, and we feed them through a lookup layer, and we get a sequence of word embeddings, okay? And then you say, fine, right? We put this sequence of embeddings into a multi-layer perceptron, we got the class label. But wait, the problem is the size of this input vary, right? We can have a 3 word sentence, we could have a 100-word document. So, but if we feed that to a multi-layer perceptron, we don't know how many neurons we need, right, for the hidden layer. So we need something else, right? So what is this something else? It is a sequence representation layer which takes a sequence of embeddings and finds a single hidden representation, okay? Well, you can define this hidden representation as 1,000 neurons, or 2,000 neurons, or 768 neurons, whatever you want. But this must be a fixed size, right? So once you have a fixed size, you could then feed that to an output layer. So we call this a sequence encoding layer or sequence encoder. So that's the main topic of today. So, and we basically have 4 things to discuss subsequently. So one is called pooling, one is called convolutional neural network, one is called recurrent neural network, one is called attentional neural network, okay? So these are the classical neural network architectures you can find in NLP. But maybe you say some of them are familiar to me because I learned convolutional neural network in machine learning. You will find that these could be slightly different, okay, in NLP. So after you got these sequence representations, then you can connect an output layer on top, right, of the hidden layer. So this output layer, you've already learned that. It could be just a single neuron, right? Single layer perceptron, activated by softmax. And we learned that in week 5, if you remember. So this is just a single neuron layer, okay? For multi-class classification. And we reviewed that last week. Okay, so this is a neural network. With that, we could make text classifications, and we can train this neural network using log likelihood laws or cross entropy laws, right? Provided you have a set of data with gold input and output pairs. You have a lot of documents, and each document is labeled a class label. Okay, you are very familiar with this because since week 4, you have been, right, struggling or enjoying with these classification problems, okay? You know how to train that, right? So when you have a cross-entropy loss, basically you minimize the negative log likelihood of the data set, okay? Where do these probability come from? They come from the model, right? So your loss function contains model parameters, and you can plug the gradients on every model parameter into SGD. You can train it, okay? Just like we trained perceptron, just like we trained SVM, right? It's an online learning algorithm. So later today, I will show you more variants to SGD. But the important thing is, you know, you have these different modules, right, to make text classification now. You have an embedding lookup table to worry about. You have a sequence encoder to worry about. You have an output layer, which is single softmax neuron to worry about. But last week we learned if we take back propagation rules, right, we can modularize the calculation of gradients on each layer. So you could just take a layer from your toolbox and you assemble them together, you make the classifier. All right, so that's the background. And we move on to the 4 mentioned earlier. The first one is pooling. So what is pooling? So pooling is a simple approach for you to integrate information from a sequence of vectors into one vector, okay? So pooling is the basic thing you need, right, to integrate features from word embeddings. All right, and a simple way to do pooling is to sum up every individual vector together, and we call that sum pooling. And I show you in this equation. Okay, every word embedding must be of the same size. Okay, if one is 768, the others must be 768. If one is 50, the others must be 50. So you can sum up them together. The second is average pooling. Okay, so for sum pooling, you will find that, okay, if the sequence is longer, then every element in my hidden layer will be larger maybe. Okay, not necessarily, okay, because sometimes some element might have negative values, right? But suppose that they are more positive than negative, then the longer the sequence, the larger the average value. So you can fix this by taking the average of all the input. So that's called average pooling. A third method is called maximum pooling. Okay, what do you mean? It means that for every bit in your output, right, you take the largest value, okay, among all the input, okay, on this dimension. Okay, so in other words, if your input embeddings are 50 dimensional, right, so you have to look at 50 numbers. You have to create 50 numbers in your output. And for the first bit, you look at the first bit among these 50 input. Oh, no, not necessarily 50, among this sequence of inputs, right? And you select the highest absolute value, put it here. Second bit, you look at all the input embeddings. The second bit, you take the maximum here, as written in the equation. So you repeat that for every element, you got the result. The reverse for maximum pooling is minimum pooling, right? So these are 4 common techniques to assemble a sequence of vectors into one. And you tell me maybe averaging is easy to understand. Why do you do the maximum? Okay, we learned last week that we cannot directly interpret, okay, what every element means in your vector. But you can imagine, okay, imagine that one bit means sentiment, okay? So we learned the sentiment lexicon, right? So the more the value is, the more positive it is. The smaller, the less the value is, the more negative it is, right? So maximum pooling, okay, if you do it on this bit, it means I pull out the maximum positive sentiment, okay, in this feature. So I had a nice day. I had a great day. I had a fantastic day, okay? Maybe the sentiment of these words, they differ. You pull the most positive one, okay? So similarly, negative pooling can pull the most negative sentiment in that bit. But I have to repeat, you don't know what each element means, okay? It's just a manually coined example to show you. Okay, so these are easy to compute, and they don't have model parameters. But you still have to define the backpropagation rules. Why so? Because you don't worry only about yourself, right? You need to worry about your previous layer, okay? So once you receive a gradient on your output H, you have to backpropagate the gradient onto your input X, all right? So that's calculus. And it's trivial to find that for sum pooling and for average pooling, these equations hold, all right? For maximum pooling, okay, it's not so obvious. But you can look at the gradients bit by bit, okay? So basically, for every bit, okay, the gradient back propagates to the input, which contributes to this bit, right? So if the maximum value, okay, if the value of the output, the third element, comes from the, okay, first input vector, then the gradient on this bit will back propagate to the first input vector, right? So that's what this equation says, okay? So a vector will receive a gradient on the element, okay, that contribute to the output vector. That's the maximum pooling. So similarly for minimum pooling. With these rules, we can complete the pooling module. All right. So next, convolutional neural network. So pooling has a pooling is very simple, straightforward. Okay, it can assemble a varying size list of vectors. But pooling is a little bit like a bag of word model, in the sense that it just aggregates features, right? It doesn't consider the word order, for example, because you're treating each word similarly in your equation, right? And also it doesn't consider n-gram features. Okay, every word is on its own when you do the aggregation. So convolutional neural network extracts n-gram features, okay? So all these neural networks are built using the multi-layer perceptron we learned last week. And convolutional neural network, the input is a sequence, okay? I denote it as x1 to xn. Now the output is another sequence, h1 to hm. So this value of m is determined by, okay, your convolution size. What do I mean by convolution size? So basically, convolutional neural network extract features from n-grams, okay? And this n is a fixed value. We can denote that as k, okay, k-gram features. So in this picture, I showed you a CNN that extracts trigram features, right? So, and you can see that the neural network works by taking a sliding window of k equals 3, okay, from left to right. For each sliding window, we basically calculate a representation of the k-gram the window covers. And this is called a convolution filter. For example, x1, x2, x3 is a trigram. And we calculate a feature over these three words. And x2, x3, x4 is another trigram. We calculate another feature. The way we calculate these features is just an MLP. Actually, it's just a single layer perceptron with linear activation. It's shown here, okay? And we give it a name, a convolution filter, by following the research on computer vision. And then this H integrates information over the k-gram it covers, okay? So how does this xi to xi plus k minus 1 work, okay? So it works just like for n-gram language modeling. You just concatenate the embeddings, okay, into a 3 concatenation form, and then you pass that to a matrix. And that's it, okay? in summary, we have a convolution filter for x1 to x3, one for x2 to x4, etc., until the last trigram, we have a convolution filter. And each filter is a single layer perceptron, okay, that calculates a hidden representation of the trigram. We have to think about backpropagation rules given this forward computation equation. The backpropagation rules need to worry about the internal model parameter and the input, right? So from what we have here, there are two salient model parameters. One is W, one is B, okay, the bias vector. So we calculate the gradients for them. Once we have the loss, the gradient on the output H, okay, we can calculate the gradient on W as the output layer loss times, okay, the concatenation of the n-grams, the n-gram representations. So this part is the output loss times a trigram, okay? And we need to sum up all these trigram loss as the loss on the weight matrix, okay? It's quite obvious, but if you don't see that immediately, you can do some derivation exercise afterwards. So similarly, for the loss on B, we can calculate it as a sum over all the convolution filters. For these backpropagated loss on the input vectors, the equation is shown there, and I encourage you to derive them by yourself. You say, okay, with convolutional neural network, I extracted n-gram features here and there, but that's another sequence, right? So that's not a single vector. What could we do? So normally, you add another aggregation layer. For example, after you extract all the n-gram features, you add another pooling layer, and you create a single vector representation. Now, with this, we create a first neural network that doesn't rely on a manual representation of the input document, right? So no TF-IDF, no counting-based document representation, but just everything is automatic. We map all the words into word embeddings. We extract a sequence of trigram features, and we do a pooling. All right. So if we compare that one with this one, we can immediately find some differences. All right. So the CNN features, they are dense and low dimensional. You normally will see a 1,000 element long, right? Convolution features, or even smaller. Compared with this one, tens of thousands of elements long. If you use bigram features, it's tens of thousands squared, right? And if you use trigrams, it's even more, okay? But of course, you cut a lot of zero values because the real feature vector can be smaller. But it's all dense and lower dimensional compared with the sparse vector we had, okay? And more importantly, they're automatically learned. So you don't manually define them. And they are adjustable during training, which means given the same sentence, okay, and after one training iteration, your convolutional representation will be a vector. After a second training iteration, they will change, right? Because your model parameter changed. So your input representation will change if your model parameter change. So this one is fixed. Okay, it's manually defined. So in that sense, I say it's dense, low dimensional, and dynamic. Okay. It doesn't depend on the input only, but also depends on your model. All right. So this is CNN and pooling. So let's move on. So the third one is called recurrent neural network. So CNN is better than pooling. We have n-grams now. Okay. So and you can be clever. You say I can have a trigram CNN, I have a bigram CNN, and I have a unigram pooling, and I extract a lot of hidden vectors using all this kind of heterogeneous neural network, and I can concatenate them together, right, for rich features. And that's what people did in the research field. But that's not completely powerful yet, because we extracted n-gram features, but we don't extract a long-range feature, a feature that spans from the first input word to the last input word. Okay. Can we do that? We couldn't quite do that with manually defined features. It's too difficult. Okay. But maybe we can have a neural network to do that, right? Just by defining a new structure. We want to extract features, okay, that cover the whole sequence word order, okay? I say from word 1 to word n, okay, and with that sequence, you know, n-grams cannot cover that. How do I do that? So maybe we could define a recurrent state, okay? So it's a hidden vector. The hidden vector initially takes maybe a random started value or as a model parameter, right? And then we keep on combining this hidden vector with word 1 representation and word 2 representation, etc., from left to right, okay? Each time we use a elementary neural network structure to integrate the current state and the current input to create a new state. If we do that, okay, towards the end of this neural network, we will have a state that remembers the whole sequence information. And that should be better than convolutional neural network, okay, in terms of coverage. So how do we define this recurrent function? Okay, so similar to convolutional neural networks, we want every step, okay, to be exactly the same. We share model parameters on every step, okay? So we can conceptualize this as a state machine, you know. It works like this. So the state machine has a current state h, which is a vector, okay? And at every time step, it will take the current x, or the current input embedding as input, and integrate information between h and x to create h for the next time step, right? So you only need one state that is dynamically updated. Okay, so that allows us to say every step is the same. We have the same model parameter. And how can we define that? Of course, we use the simplest neural network structure we learned, which is a neuron, right? We learned that in week 5. And that's similar to CNN, okay? It's just that I added a non-linear activation function, f here, okay? So, so last week, we discussed several nonlinear activation functions beyond softmax and the sigmoid. For example, ReLU and 10H, right? So here, maybe we use 10H for example. So every step will be a 10H of this Wx plus b. And you say, here you write a slightly different equation compared to CNN, right? For CNN, it's like you first integrate the input n-grams into a longer vector and then multiply that with a matrix. Why here you don't first concatenate ht minus 1 and xt and then multiply that with a w? I write it here because by careful derivation, you see these two are the same, okay? I just cut this bigger w into two smaller parts. And one smaller part multiplied with h, another smaller part multiplied with x, okay? It's the same as if you put the two parts together, you multiply that with h plus x. Okay, it's easy to see, right? Okay. So some papers write it this way, some papers write it that way. You should be familiar with both. All right, and that's okay, but you wonder, okay, you're telling us something different, okay? Because for pooling, for CNN, for NLP, everything is obvious to us, right? It's just a forward computation process. But now you have a loop in your neural network. What you're doing is you are connecting your output, right, back to your input. That's a loopy neural network. We're confused about this loopy neural network, okay? So how can we conceptually understand it? How do we understand the recurrent process, okay? But I'm saying that this conceptual loopy neural network is just a trade-off between space and time. If you only have one state, okay, and you dynamically update it with one word input, second word input, third word input, it's a recurrent process. But if you imagine, right, you have a vector to remember h1, h2 until hn, okay? It's a trade-off, you trade time for space, okay? If you have enough memory, then this loopy process will become a feed-forward process, okay? Assuming that you have enough memory to remember the historical hidden states for every input, right? Okay, if you have enough memory, you can do that. So current LLMs can handle like millions of words in history, right? But of course, it uses a different neural network structure. We will learn that a bit later. Okay, so this is called the unfolded structure. This is called the recurrent structure. These two are equivalent. With that, you say, I want a single H to represent the whole input. How can we do that? You can do that by either using the last hidden state, Hn, okay, as a representation of the whole sequence, or you can use a pooling layer on top of all these hidden states. Just like when you do the pooling for CNN, okay? All right. So, next we discuss training. You say training is easy because for RNN, right, if you use the unfolded version, then every time step is just a single layer perceptron, and we just have a multi-layer perceptron, maybe a longer, right, dynamic-sized multi-layer perceptron, okay, in this direction, it grows in this direction, okay. If we tip it up, okay, maybe it's a multi-layer perceptron. It's just like a tree with only one side having branches. So the backpropagation rule is nothing new. So we don't have to worry about the backpropagation rule. Okay, but I still want to say something because this is a dynamic neural network. the gradients will have some interesting issues. For example, let's assume the activation function is tan h. Then you have the layer structure as I show you in this equation. And then the backpropagation rule is very straightforward. I have a few equations listed in this slide, but the first one is a backpropagated gradients from the output vector to the input vector, okay? The other parts are the backpropagated gradients on model parameters, okay? As I said, I split the big W into two W's, one for H, one for X. And as a result, you will have these few backpropagated, the few gradients on the parameters. Sorry, let me correct myself, okay? The first two are backpropagated to the input vectors because the input has H and X, right? And the last three are backpropagated to W and B, your own model parameters. So this is nothing surprising to you. It's just that you have to handle the gradients for the tan h function, okay, which I leave it for you to derive. But the interesting thing is, let's look at the gradients over different layers. The neural network grows with longer input sizes. So if you accumulate the backpropagated gradients, basically you accumulate that from hn to hn minus 1, right? And then to hn minus 2 until h1. This is a long chain of backpropagation. And in each layer on H, you multiply something, right? You multiply this W transpose to something else, okay? And in the end, if you accumulate that back to the input, the accumulated factor of W transpose will be to the power of your size. And what's inside is also, so this is a product, The terms inside here, the Hadamard product terms, will also grow with the size. Okay, I copy that equation to this slide, and you see that the power term grows with t, the lower t, okay? There could be issues. Imagine, okay, so the norm of your WH, okay, is small, okay? It's a small value. And if you accumulate that matrix to the power of t, this whole thing can tend to 0, Every element in this will tend to 0, which means your gradient will be smaller and smaller when you backpropagate from the last word to the first word. All right? I'm assuming that you connect the last word to the output layer. Okay? So this is called gradient diminishing. Okay? Gradient diminishing. So something even more severe, So if the norm of this W is large, more than 1, then if you multiply the same matrix t times, this thing can grow larger than your numerical capability, causing numerical overflow. This is called exploding gradients, okay? Gradient explosion. So neither situations is what we want, okay? So I just explained W to you, but there is these products as well, right? Inside the product. So HT will also play a role. How can you solve gradient explosion and gradient diminishing when the number of layers of your neural network grows? there are several technologies, okay? So one is called truncated backpropagation through time. Why through time? Because your layers, they represent time, right? Recurrent neural network. You can just backpropagate the gradient for a few fixed steps, and you stop there. Okay, but in that case, you don't train the neural network as accurately as if you backpropagate the gradient until the first layer. The second, if you initialize your W properly, okay, then maybe your training is more stable, of course. Third, you could also improve the neural network architecture to allow more stable training. Okay, we will talk about the neural architecture change later. And there's some other technologies to improve SGD, of course. We will cover that. So before we move on to the stabilization, let's talk about another issue for RNN. You know, for RNN, you run the neural network from left to right. So every state will remember only history information from the first word until the current word, okay? But it doesn't remember words on its right. So when you do pooling over all these words, you get a few features. The first word, the first two words, the first three words until the whole sequence. But you don't have any information about the last word, last two words, last three words until the beginning, right? So you can fix this problem by using one recurrent neural network from left to right and having another recurrent neural network from right to left, okay? And then in the end, you got some structure like this. My input is a sequence. I have one sequence here, another sequence here, right? Okay. If you concatenate HI from left to right and HI from right to left, you know, then this concatenated vector will have information from the beginning of the sentence until this word, and from this word to the end of the sentence. Okay? So each hidden layer will contain information from both sides. And I guess these equations are self-explanatory. Okay? So you can read and understand. Then you say, for bidirectional RNNs, right, or bi-RNNs, how can you represent the whole sequence? Well, as I suggested earlier, you could use a pooling over all the hidden states, and you get information from the whole sequence. Or you can use HN from the left to right component and H1 from the right to left one. Okay, you concatenate them together as the representation. Normally, pooling works better, okay, because your gradient will pass back to every individual word in the sequence. And then you say, in addition to my forward computation, I need back propagation as well, right? How do you backpropagate the gradients? So if you look at each RNN component, the backpropagation is the same as backpropagating gradients for one direction, right? It's just that you have two RNNs. So they will have backpropagation rules separately. But then for every X, it is connected to both the left to right RNN and the right to left RNN. So it will receive gradients from both components, okay? How do I handle this? It turns out that the gradients are added together, okay? You have one backpropagated gradient in one path, you have another in another path, you add them together, and it will be the gradient on your x, okay? So that's about bidirectional RNN. So let's continue. So LSTM, long short-term memory is the full name. It's a variant of RNN that better handles gradient issues, okay? One very salient difference between LSTM and RNN is RNN just uses a recurrent hidden state, right? Uses a recurrent hidden state. But LSTM uses a recurrent cell state. And then the hidden state at every time step is calculated through that cell state. So this is the salient difference. All right. The second difference is that LSTM uses a set of gates to do recurrent computation, which I'll talk about later. Okay? First difference, cell recurrent state. Second difference, the use of gate. Let's look at, okay, the first one. For RNN, you only worry about X and H, and that's all, right? For LSTM, you worry about X, H, and C. Okay? And the LSTM step is therefore HT-CT is equal to a recurrent step, XT, HT minus 1, CT minus 1. Okay, both H and C. And as I talked about earlier, so the recurrent state is on C, not on H. H is computed from C. The recurrent step uses gates, and I draw you a picture here, okay? It's not a simple composition of CT minus 1 and XT, okay, with a single neuron. But it's sort of a gated combination. If you look at the equation on top, okay, CT is equal to IT, Hadamard GT, plus FT, Hadamard CT minus 1, okay? So this GT represents the input. Why not XT? Okay, it's XT through a feed-forward layer. I will show you later. Just imagine GT represents XT, okay? And CT minus 1 is the previous cell state, okay? So overall, this equation is still to compute the current cell state from the previous state and the current input. So it's a recurrent function. But it's not a single neuron, okay? There are two Hadamard products. You know Hadamard product means bit by bit product, right? All right. So the IIT and FT are called the input gate and forget gate, respectively, okay? And these gates, each bit has a value between 0 and 1, okay? Which activation function gives a value between 0 and 1? Is it tan H or sigmoid? Sigmoid, right? Tan H gives a value between minus 1 and 1. So IT and FT are called two gating functions. Every element in these two vectors are a value from 0 to 1. And when they multiply, okay, G and CT minus 1, they serve as water gates. What do I mean? Because this element, this vector is multiplied to this vector, element by element. It filters information, okay? like floodgates. If this is a 1, all 1 vector, then information from G will pass through, right? But if this is all 0 vector, information from G will be blocked. Okay, similarly for CT minus 1, all right? So 2 water gates, 2 gating vectors controls information flow from either the history, your long memory, CT minus 1, and the presence, your current input, okay? Do I want to look at the current input more? You open this gate, okay? Do I want to look at the history more and ignore the input? You open that gate. So these 2 gates are trade-offs, okay? So this is called short-term memory. This is called long-term memory, okay? And it turns out that by the use of gates, you handle the gradients more easily, okay? And actually, this equation is the core of your LSTM. After you understand this equation, you can understand the whole of LSTM. Now, let's explain the equation a little bit. As I said to you, G represents the input. G is actually a composition of your previous hidden state, ht minus 1, and your current input, xt, through a tan-h activation function. So that's the G value, okay? And the 2 gates, input and forget, okay, are a composition of your previous hidden state and the current input through a sigmoid activation function, as I talked to you earlier, right? And that makes sure that the G, the input representation, ranges between -1 and 1, and those gates are positive values, okay, below 1. Okay, so now we have the equation for recurrent cell. What about H? H is computed from the cell, okay? So I have another gate called the output gate. The output gate is another single neural layer with a sigmoid activation. And then the H, the hidden state, is a tan-H activation of the cell state, Hadamard, the output gate. All right, so this is the equation. In other words, H is an indirect project of your cell value through a water gate. And if you put everything together, you have the complete daunting LSTM equations, okay? So you have 3 gates, input, output, and forget. And you have a cell, you have a hidden. Okay, but their composition is explained earlier. The only thing to note is that for every gate you have a W and B, okay? And these should be different. The W and B for the input gate should be different from the W and B for the output gate, for example, all right? So model parameters are these many. Many model parameters, many more than recurrent neural network, okay? And people searching for LSTM over the internet will find this picture, okay? So it's a picturesque representation of the equations I just showed you, okay? So there's one arrow from left to right representing the hidden state information flow. And there is one below that represents the information flow from X. You know, and all these yellow sigmoid signs represent how you compute the gates, okay? And this tan-H sign represents how you compute the G representation. And you see all these additions and multiplications they are Hadamard product, etc. Okay, so if you translate this picture into equations, you have the what I just showed you. All right, let's take a small break. Okay. Now, before we take the small break, okay, I will tell you that LSTMs can be stacked in the same way as RNNs. Okay, actually, not in the same way as RNNs. So LSTM can be put into bidirectional variance in the same way as RNNs. Okay, so I don't want to explain that, but you can stack multiple layers of LSTMs or RNNs. What I mean is, if you have an LSTM, your hidden state will be a representation of the whole sequence in a nonlinear way. But if you want to find more abstract representation of the sequence, you can take the output of your LSTM as the input of another LSTM. Okay? And then your second LSTM will extract more abstract features, which is an aggregation of the aggregated hidden vectors. All right? So if that is not enough, you can stack a third LSTM layer by taking the second layer output as inputs. Okay? So you stack LSTMs in this way, you get a multi-layer neural network. And this thinking is very important. Okay? This is called stacked LSTMs. So this is the equation for stacked LSTMs. Okay? So the layer L will take the output of layer L minus 1 as its input. So the last neural network structure for sequence encoder is attention. So what is attention? Attention is a variance of pooling in aggregating a sequence of vectors. Okay? So pooling takes the sum, the average, the max, the mean, okay, for aggregation. But attention takes a weighted sum for aggregation. Okay? So all in all, attention is the sum of, okay, alpha I times hi, where alpha I is a weight. Okay? So these alpha i's are between 0 and 1, and they add up to 1. Okay? So when you're given a sequence of input, the output h is a weighted sum of the sequence of inputs, where each one is weighted by alpha I. Next, how to calculate alpha I? You need another vector called the query vector, okay, Q. So Q will be applied to this sequence H, okay, to derive a score on every HI. So when you apply Q to HI, you use a scoring function. I call it a score, okay? Score QHI equals SI, which is the weight on HI. And as I said, this alpha I need to be a distribution. Needs to be a set of 0 to 1 values that adds to 1. So a softmax function will do this, right? So you take all the scores, SI, and you put them through a softmax function, you got alpha I. And then the last step is just as I described earlier. So the overall H is just a weighted sum of all these HI, okay? So in here, all we need to solve is how do you score each HI using Q, right? So as long as you have how to calculate SI, you know how to calculate H. And there are different ways to do that. I show you 4 of them. So the first one is quite simple. It requires Q and H to be of the same dimensions, okay, same size. It's called dot product attention. So you score HI by calculating the similarity between Q and HI, Q dot HI, or Q transpose HI, okay? So that's the first way. Second, a scaled dot product attention. So, you know, for all these dot product functions, the longer the vector size, the more likely that the score is higher. So we could normalize it by taking the square root of D, okay, as a divisor. Okay, so this means that D is the dimension size of Q and H. Okay, it means that the score is more stable across different vector sizes. Or we can introduce some model parameters. Okay, for example, a general attention takes this Q transpose WH form. Okay, so this is a tensor product. So WH will give you a vector, a column vector. I'm assuming that every vector is a column vector. Okay, and then Q transpose times this WH will give you a score. What's the advantage of this general attention? First of all, you don't just take the brute force similarity score, right? You allow some model parameters to control the similarity score. Second, you know, this tensor form allows every element of Q to interact with every element of H through the tensor product. So it gives more feature contact between the two vectors. All right, so can you do more? You say, can't we just concatenate Q and H and pass it through a multi-layer perceptron? And yes, you can. So this is the last form of score calculation. V transpose 10HWQ plus HI plus B. Okay, so this is a 2-layer perceptron, right? So the first layer is a 10H activated neuron. The second layer is a simple neuron, no activation. Okay, the first layer parameters are W and B. Second layer parameter is V. Okay, a 2-layer perceptron to calculate a score. And so dot product attention and scale dot product attention require the same dimension size for Q and H. General attention and additive attention don't require this. And they introduce some additional model parameters to allow training of the scoring. Okay. All right. So backpropagation, you know, for every neural component, we need to define the backpropagation rules. So for this attention mechanism, the inputs are the H values, right? The Q can be a model parameter to train. And also for additive and general attention, the weight matrices and vectors are also trained internally. I will leave the derivation of these gradients to you. There is a more advanced attention function called QKV attention. Okay? So the idea is, originally you use a query Q, okay, to both calculate the score and, I should say the reverse way. Originally, you use this sequence of vectors H, right, to both calculate the score with Q and ask the values you aggregate. In other words, you calculate the weighted sum of HI, okay, and the weights are calculated using Q and HI. This is a little bit different from database query. You know, for database query, you have a key to your database table. And you use a query on these keys, but whatever you retrieve are the values. So this is called query key value retrieval. We could do the same. So we could find sort of a key or a representative of every HI, okay? And before we aggregate the values. So this is QKV attention. You can think about that as you have two representatives of each HI, one serving as the key for query interaction, one serving as the value for the retrieved vector, okay? And on the equation, as I show you in this box, so the score is calculated, no, actually, as I show you not in this box, okay? The score is calculated between Q and K. And the result is an aggregation of V, okay? So whatever is in this box is the original attention function. So if you carefully look between the two sets of equations, you will see that the second equation, the calculation of alpha, the softmax, is the same, okay? The first equation, you replace the HI with KI, so the key. The last equation, you replace the H with the V, okay, the value, okay? So this is QKV attention. Now, when you have one query, okay, you can get one aggregation of values. But if you have a sequence of queries, okay, you can result in a sequence of values. Of course, you say this is obvious, right? So Q is the query. When I have one Q, I aggregate the set of values, I have one H. So if I have many Qs, I name them Q1, Q2 until Qm, right? Until QL. So you aggregate the V vectors in different ways. You result in H1, H2 until HL, okay? So this is so obvious. Why do I mention that? I mention that because you can calculate L different queries in one run. If you have a GPU, okay? They can run in parallel as a matrix multiplication. You have to read this offline and figure out that these equations are right, are correct, because we don't have time to derive it together in class, okay? But since you will be able to calculate the scores, okay, in one matrix multiplication, you can run the query, L queries in parallel, okay? And that gives us a basis for deriving a new sequence encoder called self-attention network, okay? What is self-attention network? A self-attention network can be seen as a sequence representation alternative to recurrent neural networks, or LSTMs, okay? Its equation is just a QKV attention equation. I use the input sequence, okay, for the query, for the key, and for the value, okay? Let's flip back to this picture, okay? The key sequence of vector are my input sequence of vectors. The value sequence of vector is my input sequence of vectors. In addition, the query, okay, the many queries are also my input sequence of vectors. Okay? And if I run it in parallel, so in one go, I calculate a sequence of resulting vectors to represent the whole sequence. And obviously, so each output, okay, is an aggregation of the input vectors using the current input as the key, right, as the query. I use the current vector as a query to query everyone else, and I aggregate everyone else for representing me, okay? So this is the basic idea. All right, and then you say, this is fast. Because unlike RNN, we don't have to do 1 step, 2 steps, 3 steps. Just one go. But this is inaccurate. Because for RNNs, I know the word order, right? Word 1, word 2, word 3, from left to right, from right to left. I know their composition order. But here, you're just doing a bag of words, okay? You're just a bag of words. So you're much less powerful than RNNs. But wait, we can fix that. First of all, you say this aggregation doesn't have word position information, right? I do a simple aggregation. I don't know you're my left neighbor or you're my right neighbor. You don't know how far you are from me. But how about we add position information into my word embedding, right? Originally, I have X, the word embeddings, as my input, if you remember the beginning of the class. But now, how about we concatenate a position encoding vector with my word embedding vector, okay? So that when I do the query, I know my position and I know everyone else's position. So I aggregate you according to relative positions, absolute positions. How do you represent a position into a vector? Okay, you say, I can do it the same way as word embeddings. I can randomly initialize a vector for every integer position, and I can train the position embeddings as my neural network parameters. Okay, that's one way. But it turns out that a simpler way works as well. So you just hard code a set of vectors representing each position. Okay, how do you hard code a vector? Here I show you the one way of doing it. Okay, so here Pij represents the vector for position I, the ith word, okay? Then J represents the jth dimension or the jth element in this vector, okay? So every element in the position encoding is hard-coded using sine and cosine functions, as I just showed you here. These are just some hard rules. I don't have to explain them, okay? But using these rules, you will calculate one distinct vector for each position. And those positions can range to infinity. So when you use X concatenated with P, okay, as the new word embeddings, you solve the word order issue. Now we have order information, but we still have one limitation, which is we are linear. You know, we are just a weighted sum of my neighbors, okay? But RNN is nonlinear because, well, I can do nonlinear activation one word after another. So I capture more semantic compositions. In addition, as I just showed you, you can stack LSTM one layer after another, right? And you get more nonlinearity. But if you just stack linear aggregations, no matter how many stacked layers, you're still linear, right? So we have to introduce some nonlinearity to it. How can we do that? Okay? I can do that by also improving my representation a little bit. You know, currently I'm using myself as the query, right? And I'm using myself as the key. And I'm using myself as the value. Can I find 3 different representatives of myself? Okay? One as the query, one as the key, one as the value. Can we do that? If I do that, I, of course, have more flexibility. And can we do that by also introducing some nonlinearities at the same time? Okay? Can you think of a way to do that? The solution is, for every input vector, okay, I can use a multi-layer perceptron to map me into the query vector. Use another multi-layer perceptron to map me into the key vector. Another one for the value vector, right? So because the model parameters of the 3 MLPs are different, I get 3 representations of myself, right? So I can use the query representative to query the key representative of everyone else and aggregate the value representative of everyone else. That can be written in this equation, okay? So I have a Qi for query, Ki for key, Vi for value by 3 different projections. And in each projection, I have the position embedding as my input component, okay? So in the end, the attention becomes attention between query and key and V, okay? No longer between the naive representation. That's my self-attention neural network, okay? It's nonlinear, it has position information, it can stack multiple layers. The advantage, okay, of self-attention neural network as compared to recurrent neural network is the representation of every input can be calculated simultaneously, okay? So it runs faster. And empirically, it also works competitively. You say, wait, okay, I'm doing my project and I'm using transformer, and what you described reminds me of transformer, okay? I will talk about transformer later in another class, which is an extension of the naive self-attention neural network we discussed today. All right, so as the last part of today, I have to talk about training of neural networks. Remember, we built RNNs, and we looked at the backpropagated gradients, and we found that they can explode, okay? Because they can explode, we developed LSTMs. But even LSTM gradients can explode. I tell you, my student used to show me to his computer, and I saw a lot of NANs, not numbers, in the gradients, okay? So I say the gradient exploded, okay? How can you fix that? Well, there are different ways to solve the gradient issues. I first show you a few on architecture changes. Remember last week we talked about the shortcut connection, right? So I give you the equation here. So the input is x. The neural network is g of x. Okay, g is a nonlinear activation. So a shortcut connection means h is gx plus x. Okay. And I told you that this one works better for building n-gram language model. Okay. Why is that so? And today we can view that as from a gradient perspective. So when you take the gradient, right, over G, you know, G can be many, many, many layers. Can be an RNN, or no, maybe not an RNN. MLP of 10 layers, for example. Then H will not backpropagate to X, okay? It can diminish. So adding this shortcut connection, okay, reinforces the gradient on X. Because you know the other path just copies the gradient on H to the gradient on X, right? It's just a copying. So your X will always learn and respond to output loss, okay? This makes your neural network better. Shortcut connection. There's another technology called layer normalization. What is it? Okay. So before I introduce that, I will have to remind you again of the difference between CNN features and the discrete features. Okay. So in the first few weeks, we spent quite some time discussing discrete features, feature engineering. Okay. But the CNN features they're automatic. But every time you train a neural network, the feature representation of your input will change. Okay. Suppose I'm the output layer. You guys, okay, how many layers? 5 layers are the, okay, CNNs, okay, 5 layers of CNNs. I don't see the input, right? I see you. So the first time, your input is still, I like NLP, okay? I see features from you guys, okay? And I train you, or I'm also trained, okay? Second time, the input is still I like NLP. But you guys give me a different representation. I will see, okay, this might be a different input because I never see the input, okay? I only see what you give me, right? Your CNN. Every time I train a neural network, I see a different feature. So this is very unstable. This means, okay, a slight change in one of you will cause butterfly effect on me, okay? A very unstable. So how do I stabilize the internal representation? Okay? So there are different ways you stabilize the representation. So one common way is called layer normalization. Okay? It just normalizes the representation vector by taking, okay, the mean and the standard deviation from a sequence. Okay? In other words, layer normalization is a method, is a technology that stabilizes vectors over a sequence, right? So if we are a sentence, right? I have a sequence of vectors. I stabilize our representations within the sequence. So this is called layer normalization, right? So without further assay, I guess you can just see the equation, okay? So, so this mu is the mean. This sigma is the standard deviation, right? So every vector is z, okay? So if you use z minus mu divided by sigma, you have a normalized version. I don't have to explain that, right? But then why do I introduce this alpha and beta? Okay, these are two hyperparameter vectors. Okay, I use alpha to multiply this normalized mean. Okay, I call alpha gains. And I use beta to add to these normalized vectors. I call beta biases. Okay, turns out that if you use these two hyperparameters, you have more flexibility. Okay, so this layer normalization also stabilizes training. A third technology is called dropout. Okay, dropout avoids overfitting. With neural network, you know, we have many, many model parameters. And we are very nonlinear. Because we're so powerful, we can easily remember the training instances. Okay? We're so powerful that we can remember every training document without forgetting a token. So that also means that we can draw a very, very fine-tuned hypersurface, you know, to separate training examples, okay? Which leads to overfitting. Okay, because we might be tailored to nuances in training data, okay, which don't generalize. How can we avoid overfitting with powerful networks? So dropout is a very simple and effective strategy which is used in almost every neural network during training. The idea is you have an input representation, okay? Now, I deliberately make some noise, okay, in your input to make you look a little bit different from yourself every time I train you, okay? Now, how do I add noise to the input vectors? Dropout just randomly makes several bits to 0. Suppose your input vector, okay, for every word embedding is 1,000 elements, right? I just randomly choose a proportion. Maybe the proportion is 0.5. Maybe the proportion is 0.9, okay? Maybe it's 0.1. This is a hyperparameter. I randomly choose this proportion of the 1,000 elements and set them to 0 during training, okay? In other words, every time I see only part of the input features. I train my neural network to make decisions on a part of the inputs, not all the features, okay? And next time I train the neural network to make decision on another part of the input features, okay? So there will be less risk on the neural network overfitting on certain feature combinations, you know, because every time I only see a few features. In equation, it's like that, okay? I have a mask vector M, and I use this mask vector to do bitwise product to my input X. So for every training iteration, I just randomly set a proportion of these M vectors to 0 and the remaining to 1. Okay? So this is called dropout. Dropout can be applied not only to word embeddings, but also to hidden vectors, okay? During training. During testing, you don't have to make dropout. It doesn't make sense to do dropout during testing, okay? So these are the architectural changes. Now we're ready to improve SGD. So do we need to improve SGD? You say, it's so simple and effective. In the center of SGD, okay? I already omitted, you randomly initialize your vectors and go through the training examples by several iterations. You're already tired of that. So in the center of SGD, okay, is a parameter update, all right? If I take the parameters as theta, you know, and I take the gradient of all the parameters as g, SGD will just do this. Theta is equal to theta plus eta g. So this eta is the learning rate. Okay? So in this SGD, we can improve a lot of things. The first thing is, what if G is huge? What if G explodes? Okay? Then a very brute force way is called gradient clipping. Okay? I just set a maximum bound to your gradients. Don't update model parameters beyond that. Okay? So if your gradient is more than that, just reduce your gradient to that. So gradient clipping. A second way to improve SGD training is, in the beginning of my training, my model parameters are random. So I want to go down the clip quickly. I can have larger learning rate in the beginning. But in the end, when I'm near to the valley, the bottom of the valley, I don't want to stride. Because if I take a large step, I might go to the other mountain slope, okay? And next time I run back, and never reach the valley. So I need to reduce my learning rate, okay, in the end. So one strategy to do that is learning rate decay. So basically, I change my learning rate eta. I make it smaller and smaller during training, okay? So a naive way is to step decay. So which means every step I reduce a fixed size, okay, until I reach a very small number, I don't change it anymore. So this is called step decay. So one, a smoother change is exponential decay, okay? You take an exponential curve to reduce this learning rate, all right? So, but it turns out that if you have a larger learning rate in the beginning and you have a small one in the end, you train your neural network stronger. Okay. I just mentioned to you, okay, towards the bottom, you might find situations where you take one step towards that direction, and one step towards that direction, one step towards this direction. You oscillate, okay? That's a phenomenon, okay? You might not solve this by taking learning rate decay. So a second strategy is to take momentum, okay? So you take the gradient as acceleration, and you take the previous, okay, accumulated previous gradients as a velocity, okay? So rather than using G to directly update theta, okay, you accumulate the previous G into a vector called V, as I show you in this equation. And you use two hyperparameters to control the ratio between the previous velocity V and the current gradient G, okay? This gamma and eta, they are hyperparameters. And when you update your model parameter, you use V rather than G, so that there's more chance, okay? Your previous velocity goes in one direction, so a change in the gradient at one time step doesn't change the trend, okay? So this is called momentum. That's still not the end. That's still not the end. Because what I say, okay, is a change of learning rate or the application of momentum to all the parameters, okay? I treat every parameter equally, okay? But when you train a neural network, some parameters might converge faster. Other parameters might need more adjustment, okay? So can we set a separate learning rate for each model parameter differently? Okay. And also, we want the learning rate for each model parameter to be big at the beginning and small in the end. Okay? All right? And then the third thing, how do we ensure that the learning rate of every model parameters is controlled differently? Okay? I want to reduce the learning rate of each model parameter according to how much I have changed the model parameter. All right? With these three principles, there's AdaGrad, the algorithm. First, let's look at this SGD update rule, okay? Theta is the model parameter, G is the gradient. Now, when we have 1 for each parameter, I can add I to the subscript. So theta I is the ith model parameter. And Gi is the gradient for the ith model parameter, okay? And how do I control the learning rate? I do that by accumulating the square of gradients, okay, into a special model, a special variable called SG, okay, accumulated gradient. And I update the ith parameter by changing it using 1 over the square root of the accumulation as the learning rate. Okay? Why 1 over the square root? Because the more I updated this model parameter, the smaller I want the learning rate to be. Okay? Why do I add an epsilon there? Because, sorry, in the beginning, this thing might be 0, so I don't want division by 0. So I need to add a small number, epsilon. Okay? All right. So this is AdaGrad. It's a very important contribution to changing SGD. Okay? I have a model, I have a parameter-specific rate. All right. But AdaGrad also has some issues. Because, you know, if you accumulate this thing, constantly accumulate this thing will become so large that your model doesn't train after a few iterations, right? And also in the beginning, the G squared in the beginning will greatly affect your learning process. So a second variance called RMS Prop, okay? It addresses these two issues. So the basic idea is not to accumulate over the whole history, okay? But introducing a forgetting factor. So I use EG squared as a different name for SG, okay? For the accumulated gradients. But as you compare AdaGrad with RMS Prop, I introduce a hyperparameter here, rho, okay? Rho is between 0 and 1. This is a decaying factor, right? So I use rho to multiply these accumulated square gradients so that the influence of history gradient will gradually diminish and your accumulated gradient square will not be so large as to lead to 0 update, okay, gradually. Okay, so this is the only difference. This is the only difference between AdaGrad and RMS Prop. And again, you accumulated this square root of this EG square, and then you use 1 over this RMS, okay, root mean square as the learning rate. Okay, this is the second variation. The third and last SGD variant we discussed in class is called Adam. Okay. Adam is also an extension of AdaGrad. Okay. It uses the thinking of RMS prop. Okay. I accumulate history update. But in addition to this history update, I also introduce momentum. So it's an integration of momentum and RMS prop. The equation is shown here. Okay. I have G as the gradient, and I have a velocity. The velocity is an accumulation of G. Okay. You can think about it as first order momentum. And I have the root mean square from RMS prop, right? This serves as a second order momentum. In other words, I accumulate both G and G square. Okay? How do I use G? How do I use the accumulation of G? I use the accumulation of G or V to replace G. Okay? So when I update my model, I use the momentum rather than the current gradient for the update. Okay? So what is the use of RMS? Okay, it's the same as RMS prop. I use 1 over that as the learning rate. All right. So it's quite easy to understand. So if I compare Adam with SGD momentum, I added a root mean square to have a learning rate for each parameter, right? So if I compare Adam with RMS prop, I used V to replace G in the update. So that's an integration of both methods. But there's a small trick on top of that. It turns out that we have some model parameters, this decay factor beta 1 and beta 2, right? To forget the previous values. And we want the beta 1 and beta 2 to be as close to 1 as possible for Adam to work. And that leads to a sort of cold start issue because the initial accumulation is weighted by 1 minus beta 1 or 1 minus beta 2. Okay? So a simple analysis, which I don't have time to show you here, shows that if beta 1 is close to 1, then Adam is biased towards 0 parameter update in the beginning. As a result, I fixed the equation a little bit by dividing 1 minus beta 1 to the power of t, okay, to this V accumulation. And also, I divide 1 minus beta 2 to the power of t to RMS. Right. Adam is used very frequently in model training nowadays. All right. But it's not the only way. For some other models, SGD with momentum works better. And with each training method, there are so many hyperparameters. How do I fix them? Okay. So there are 2 general strategies. One, if you have a lot of GPUs, you can do grid search, which means you can find a set of hyperparameter values and you try each combination. This combination will be like a grid. But nobody has enough GPUs. So you have to have some heuristics or random search. Okay? As I mentioned to you, the choice of optimization method is another hyperparameter which you need to try out. Okay, so let's make a summary. Today, I basically discussed 2 things. The first thing is different method to encode a sequence of vectors. Okay? The second thing is how do you improve the training of neural networks? Okay, which turns out to be much more difficult than linear models. All right. So from next week onwards, we will continue our journey for neural NLP. See you.